Assalamu alaikum all. Today we are going to discuss chapter 0 of this book, and our topic is Introduction to Programming. In today's video, we are going to discuss binary numbers, hexadecimal numbers, and decimal numbers, and and some of the logic operations like and, or, not, XOR, and NAND and NOR gates. And then we are going to discuss a little bit detail about memory and CPU, that how CPU is interfaced with the memory, and how does a CPU work. Starting from the binary numbers. Binary numbers are the numbers whose base are zero are is two. Like only two numbers can be represented in binary. They are 0 and 1. So some let me show you a table here. So there are about four ways to represent any number. It could be in the form of binary, octal, decimal, and hexadecimal. The base of binary is 2, the base of octal is 8, base of decimal is 10, and base of hexadecimal is 16. In routine, numbers which we count are normally in the decimal. I think this would be the best option for you to see. Here you can see these are all of these numbers in hexadecimal, their corresponding number in decimal, in octal, and here in the binary. We can convert any number from one number system to another. To convert any the base, its base is 10, so it is decimal number, and we have to convert it to base 2. It means that this conversion is from decimal to binary. uh, to 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 convert any number from decimal to any of the number system, we divide that number with the base of which we want to convert, and save the remainder. Here we want to convert into binary, the base 2. We divide this 25, the decimal number, by 2, and our remainder is 1. We save these remainders. The Then we again divide this 12 by 2. We continue dividing this until it gets 1. This 12 by 2, and it gives us 6, or the place where the dividing is not possible. Furthermore, we go till that point. The dividing these and remaining, and saving this remainders, we get this number. This, we have to start from the bottom to top, like we write in this way. From this one is would be the most significant bit, and this is the least significant bit. In this way we can represent this decimal 25 in this binary 11001. Moving further, we can also convert from binary to decimal by power series expansion. In power series expansion, we do these steps, like for this number we write this from right to left in this manner, and we divide multiply these all by 2. Then we assign the powers to 0 in the increasing manner from top to bottom. Like here it is 0, 1, and it is increasing till number 5. And then these would be the outputs, and we add, and after all we add this output and gets 53, which means that the corresponding value of this binary number in decimal is 53. Uh, Here are some of the more examples of conversion from decimal to binary. We can also convert from one system to any of the other system. Like here, for example, we are converting from decimal to hex, and hexadecimal to decimal. Here's the example. Let me tell you a trick. Hexadecimal is always of 4 bits. Hex is in 4 bits, and octal is in 3 bits. Here, when any of the number is given into in binary and we have to convert it in hexadecimal, we make the pair of 4 bits from right to left. Here, this one would be the first group, this is the second group, and this is the fourth group. If any of the number remains here, we add 0, we put 0 at most left side in this way. But luckily, there are no remaining, as these are the total numbers are is the multiple of 4. So, according to this table we have seen here, this binary number corresponds to 5, 5 hexadecimal. This binary corresponds to this f hexadecimal, and this binary corresponds to this hexadecimal. In this way, this combined when these numbers are written in combined form, this 9f5 with the base 16, it is the equivalent to this binary number. We can also convert any hexadecimal number to binary in the same manner. This is the table given here. To add the binary numbers, they are added in simple way, like 1 plus 1 is 10. So 0 is written here, and 1 plus 1 gives us 2, which is in binary, it is 1 0. We put 0 here, and give 1 as a carry here to the next side. Here 1 plus 0 is 1, so we write 1 here, and after that 1 plus 0 is 1, 1 is written here. Here again 1 plus 1 is 2, which is in binary is equivalent to 1 0. This is in decimal, and this is in binary. We write 1 0 here. If we convert this binary into decimal, it gives us the same answer. Like this corresponds to 13, this corresponds to 9. When we get the sum, this whole number with the base 2 corresponds to 22. We can also get its complement. The complement is used for to get the negative of any number. In this way, like we flip all of the entries and then add 1 to the final answer. Then we can also perform hexadecimal addition and subtraction. This is very complex and separate topic, we will discuss it later. And here's description of the logic gates. We are going to discuss logic gates here. They are of many, about 3 to 4 types, and or twisted buffer inverter XOR gate. The logic gate. This is a truth table of the logic gate, and which gives output one only when both of the inputs are one. Otherwise, its output would be zero. As we have two variables here, the possible combinations would be two square, which is four. Here, four combinations are made here, and their corresponding outputs are also written in OR function. If any one of the variable from both of these is one, its output gets one. This is the symbolic representation of OR gate, and this is the representation of AND gate. In the tri-state buffer, we can it has this enable pin and this one input. When this enable is zero, This output would be unknown, and when this is 1, anything placed at this x would be replicated to y, and then it will be there would be the inverter is the complement of any entry. Like if the input is 0, its output gets 1, and if the input is 1, its output gets 0. And for XOR function is basically as equivalent to a bar b plus a b bar. It is also written as a XOR b. When both of the inputs are different, its output is 1, and when both inputs get same, its output will get 0. And here is the NAND gate. It is just opposite of the AND gate. Like its output would be 0 when both inputs are 1, and otherwise its output would be 1. And this is NOR gate, which is totally output of the OR gate. If When both of the inputs are 0, its output would be 1, otherwise its output is 0. Here we have the circuit of this adder and subtractor. We have here two variables x and y. This is the whole function of the carry. This is the function of the sum. In this using the k maps and functions and simplifications, we can draw these circuits. The flip flops are the storage device which could be of many types. The truth table of the D flip flop is written here. It has this input D and the output Q and Q bar. Here is the clock pulse, that when this clock pulse comes, the anything placed at the D will be replicated to Q. Q in the When Q is 1, it is the set state. When Q is 0, it is the read set state. When clock is 0, no, the outputs will not change. It will not depend on this input. Now we are going to discuss about memory. The topics we are going to cover in this are internal organization of computers, its different parts, and how these parts are connected to the CPU, and how does the computer work. The computer mainly has three parts: CPU, memory, and inputs and outputs. Like inputs, for the inputs we have the input devices like keyboard, mouse, and sensors, and for outputs we have LCD printers, hands of a robot, and we can get output in many forms from a computer. uh, Memory, everything that can store or retain and recall information. Like it retains the information that once we stored in it. uh, these could be of many types, like a hard disk, a piece of paper. Like if we write anything on piece of paper, it will be retained and stored. So it is also a memory, that there could be electronic memory in the form of hard disk, floppy disk, USBs, etc. It's Every memory has a specific capacity, the number of bits that a memory can store. It would be its capacity. Its organization is written in two parts, the number of locations into the number of bits of the data. Like here, 128 locations are here, and every location has 4 bits of data. Here, 128 is the uh, here is a 2 raised to power x, where x is the number of address lines we have for this memory. The exact time would be the time that when the memory is commanded to gives any output, how much of the time it takes to get data from the memory. uh, Here are some of the example for the memories. For example, RAM, floppy disk, hard disk, and then there are two types of memories: ROM and RAM. One is read-only memory, and RAM is random access memory. Basic difference between these is that ROM stores the data permanently and it retains the data even if we disconnect the power. And ROM and RAM stores data for temporarily and it loses its data when we remove the power. Here are some of the types written of these ROM and RAM. Uh, One time you can this is the first type of ROM, mask ROM. This ROM performs only the specified function specified by the programmer or the IC manufacturer. PROM is programmable ROM, which we can program, but we can only program it one time. Once it is programmed, the we cannot program it again. UV-ROM is a ultraviolet EPROM, erasable programmable ROM, which we can also erase and rewrite the program. The data, the program written on it can be erased by ultraviolet radiations by keeping it in the sunshine for about 20 minutes, and they are the by just by exposing it to UV radiations to remove the data from it. In this way, the entire content of ROM is erased. The ROM here, the read-only memory is also of electrically erasable programmable ROM, from which we can erase the already written program by giving an electrical signal. Here's flash ROM. So I have to repeat that. This the this EEPROM requires the address of the place of whom you want to erase the data. Like it cannot erase all of the data at once. We have to give the address separately of all of the locations. But in Flash ROM, we can erase all of our entire data just at once. Now discussing about the RAMs, here's the static RAM. It is made up of the flip flops and is very much fast. But as it is fast, it is expensive. The dynamic RAM is made by using a technology of capacitors, and they have less power consumption and high capacity, but they are slow. The non-volatile RAM is made up of battery, control circuitry, and SRAM. Its advantages are they are very fast and infinite programmable cycle. Like we can read, and we can change the program or erase the already written program at any time. Its disadvantage is that it is very much expensive. Now let us discuss what is CPU and what does a CPU do. A CPU executes the set of instructions given to it and executes and gives us the required output. Uh, but the CPU takes the instructions in form of lines. First, it follows the instruction given in the first line, then move to the other, and then in this way the cycle works. Here is the block diagram of a memory. It has uh, it has it has these data lines. These are the address line. This is the write enable. As the bar is placed here, it is active low. Like when we give zero signal to it, it performs its functionality. Here we have output enable, and this is chip select. Chip select just means to select this chip for its working. For to write in the memory, we just active low the pin write enable, and to read the memory, to read any data from the memory, we select this output enable by giving active load to this pin. The the memory is connected in this way to CPU. CPU, the chip select is always given one, like the chip is always selected, and the data is transferred between CPU and the memory, and CPU only gives the address to this memory. We can perform two functions on the memory, whether we have to read or we have to write. to write on a memory, we give the address of the place where we would like to write, and then we have chip select. Then we give active low signal to chip select pin, and from the data pins we give the data which we want to store at this address, and then we enable this write enable pin by giving active low signal at it. Here, this data gets stored at this address by, but we have to keep this output enable pin give high signal this time, so it would be inactive. To read from the memory, we just keep this write enable pin high, so it would be non-functional. The the chipset is already selected and address is given from which we have to read that data, and output enable pin is given zero signal as it is active low, and the data is given at the as the output. This is the access time taken by the memory. Now, how these all are connected to see to the CPU is made with these all of the functionalities, all of the components. It must have to perform its functions uh, in the form of inputs and outputs. Like it must have many of the pins to take inputs and give outputs. Now, let us discuss how we connect our CPU to these inputs and outputs. Here we one is the address bus, data bus, and control bus. Whether we have to write or read on the memory. This is the way in which we connect our memory, CPU, and our inputs and output pins with each other. Anything we have when we have to perform any of the function in this CPU, we just have to follow a proper sequence. Now we have to just make the logic circuit for this CS to be enabled. Like this chip, memory chip has to be selected. This is done by the system by the steps given below. Like if we have to move from address 0 to the address 15, we just separates the fixed part of the address separately, and the changing parts on the different side. Now using a NAND gate, we just represents our fixed parts here, fixed numeric parts here, and as A4, A5, A6, and A7 you can see here, and then we uh, when these all of the inputs are zero, the chip select would be one. Would be the chip select the output would be low, but the chip would be selected as it is active low. We can this is another example we given here. In this way we can design its logic circuit for to select our CS pin. In this way we can design this like we first have to separate the fixed part of the address. This is the main concept we have to do. As these are both are zero, the bubble is placed at their inputs. Now, how does a CPU work? This is main question. The CPU has mainly four parts. One is program counter, instructions decoder, ALU arithmetic logic unit, and registers. Registers, you can say that register stores the information. ALU performs any of the operation. Program counter uh, just counts the to proceed our CPU to the next line, or uh, to check the next instructions, and this is the instruction decoder that to which the information given is in hexadecimal, and it translates it to the computer that what task to perform. Now, let us consider an example in which we need our PC to perform this whole task in which we have to store this 17 any data placed at this pin 17 to this point A, and then A to B, from this, and then we have to swap the any data at A to this point B. Then from the pin 6, this 5, we have to place this 6 at pin A. Then at A we have to get A plus B, which can be done by ALU, and then at pin A we have to show this output. We have to show this output. Now our program counter counts to 0. This counter just counts this line, to consider this lines as 0, 1, 2, 3, 4, in this way, and this is its corresponding key in hexadecimal. Now for address bus 0, here is written 31H. Here, this 31 moves to the instruction decoder, which decodes 31, and which is decoded as the 17. Any data placed at this output pin 17 is to be moved to A. Our data can only be directly moved to this point A, and it can be shifted to B, C, and D. Here, 17 has 9. To By selecting the right pin, the database, the 9 is given to the database, and the 9 is according to these instructions, the 9 is placed at position A. Now our at address bus, our PC count is increased by 1. Here, this C4H is selected now, and it is given to the instruction decoder to decode its corresponding functionality. Its corresponding functionality is to swap the any data at A to B. Here you can see the data at A is also replicated to point B. Now our PC counts goes from 1 to 2. Our address bus is now 2. At 2 it is written 26H. The 26H comes to the instruction decoder. From the instruction decoder, it checks the corresponding entry. Here, it shows that any data at pin 6 has to be stored at A. Here at pin 6, we have 5H, means 5. 5 is stored at 5 will be stored at A. But PC counts 1, one more. Here, this shows that 6 to be a PC count is 6, but the address bus, according to the instruction, it is moved toward the pin 6. Our address bus is now 6. The data placed here is 5. So this 5 is given to the data bus and placed at position A. Our PC counts one more, and at point 3, the 81 is 81 in hexadecimal is written here. Instruction decoder just uh, just checks the corresponding functionality, and using ALU, the A plus B would be performed. Here in hexadecimal, our output would be in hexadecimal as E. 4 is given to the address bus where E is written. Our instruction decoder just decodes this EAH, and for this instructions EAH, the any data at A has to be given to this pin 7. Now the 7 address bus is selected here according to our instructions at pin uh, at EA pin 4. The EH data E in hexadecimal is stored at position 7. In this way, the decoder functionality is written here. There are two methods of the architecture of connecting the memory to the CPU. One is code memory and one is the data memory. Whether they have the separate buses or they have the common buses. This is the only difference in this. Thank you so much.